Take a look at these structures. Their physical purpose is to take hot industrial water and cool it down by exposing it to ambient air. The ultimate goal is to drop that water temperature as close to the surrounding wet bulb temperature as physically possible. This schematic shows exactly how we measure that cooling process. The actual temperature drop we achieve, from the hot water entering to the cold water leaving, is called the range. The gap that remains between that final cold water temperature and the theoretical limit of the wet bulb temperature is called the approach. By comparing these two measurements, we get the tower's effectiveness. It's a simple ratio comparing the actual cooling, the range, against the total theoretical cooling possible, which is the range plus the approach. If an exam gives you all three starting temperatures, finding the effectiveness is a straightforward plug-and-play calculation. But advanced exam questions will intentionally hide these variables to test your step-by-step problem-solving process. In a real-world plant, water returns to the tower from multiple distinct sources. Looking at these heat exchangers, you can see where these separate streams originate before they reach the top basin. Because they return at varying states, there is no single starting hot water temperature. This diagram illustrates our specific scenario. We have one stream returning 9,000 cubic meters per hour at 41 degrees Celsius, and a second stream returning 6,000 cubic meters per hour at 52 degrees Celsius, both merging into one tower. You cannot simply average 41 and 52 degrees because the volumes of water are different. We have to use a flow-weighted average. We multiply each flow rate by its respective temperature, add those together, and divide by the total combined flow of 15,000 cubic meters per hour. That calculates a true mixed basin temperature of 45.4 degrees. Correctly calculating this initial mixed basin temperature is the mandatory first step. If you skip this flow-weighted average, every subsequent calculation in the problem will be wrong. This schematic shows our second roadblock. The problem omits the final cold water temperature, instead providing a total heat rejection value of 45,000 tons of refrigeration, or TR. To bridge these units, we use a specific conversion formula. Range equals the TR multiplied by 3024 divided by the total flow times 1,000. Let's run the numbers. We plug in our 45,000 TR on top and our total flow of 15,000 cubic meters per hour on the bottom. We calculate an actual range of 9.07 degrees Celsius. With the range established, we calculate the final cold water outlet temperature. Subtracting that 9.07 degree drop from our mixed hot water temperature of 45.4 gives the cold water state, 36.3 degrees. Now it's your turn. You have the hot temperature, the cold temperature, and the given wet bulb temperature of 31 degrees. Pause the video here and calculate the approach and effectiveness yourself. Let's check your work. The approach is the cold water minus the WBT, giving us 5.3 degrees. For effectiveness, we divide the range of 9.07 by the sum of the range and approach. That gives us 63%. This documentation shows the industry-standard empirical formula used to find the physical water loss to the atmosphere. Evaporation loss equals 0.00085 times 1.8 times the total circulation rate times the range. While effectiveness tells us how well the tower is performing its primary job of cooling, the evaporation loss reveals the actual physical cost in water required to achieve that specific heat rejection. This cycle graphic illustrates the physical consequences of the evaporation process. When pure water vapor escapes through the top, it leaves behind scale-causing minerals. To maintain the system, the tower must continuously bleed out this concentrated water, known as blowdown, and replace it with fresh makeup water. To find exactly how much water is needed, we use these two relationships. Blowdown equals the evaporation loss divided by the cycles of concentration minus 1. Then total makeup water is simply the sum of the evaporation loss and the blowdown. When you sit down for the exam, use this exact 6-step chronological order. First, calculate the mixed inlet temperature. Second, deduce the range from the given TR. Third, solve for the cold water temperature. Fourth, find the approach. Fifth, calculate the effectiveness. And finally, compute the water losses. Mastering this deduction sequence ensures every variable is accounted for, allowing you to process raw plant data into a finished performance report with mathematical precision.